Hi everyone, today we're going to be taking a look at a forging example. For this problem, we've got a rectangular block in compression, and it will go from this initial size to this reduced size. Using the conservation of volume and slab analysis, we are going to find the average forging pressure, the forging load, and also the frictional stresses present from a certain distance away from the center. These formulas include the effects of friction for forging of a rectangular cross-section. We've got the average pressure formula and the pressure at a certain point. Note both of these use an approximation of the yield strengths here in plane strain condition. That's what that prime is for. And in this case, we were given the flow stress. We're going to assume that's for 3D. So we need to convert that to 2D plane strain. So in this case, we can use an approximation for the plane strain yield strength as your yield strength times 2 over square root of 3. And the yield strength is approximately equal to the flow stress, which we were given. But if you weren't given it, you could calculate it using the strength coefficient, the strain, and the strain hardening exponent equation. So now that we've calculated our yield strength and plane strain condition, we can go ahead and calculate the average forging pressure required to deform this. So I've just substituted the values to find the average pressure here. We found that the answer was 27.48 megapascals, and a little bit of an explanation on this formula. We compressed the shape to 100 centimeters in width, shown here, and A represents half of that width as 50 millimeters, and then H represents the height of the specimen when compressed, and that's 6.25 millimeters. These units will cancel out, and we're left with the average pressure. Next, the total forging force can be solved by finding the average pressure, which we did, and multiplying that by the final cross-sectional area perpendicular to the force. And if you look at what's actually happening, the final area that we want to consider would be this one, because it would be normal to that compression force. So the next part of the problem asks us to find the frictional stress at a certain distance away from the center. So here is x equals 25 centimeters. We are right here along the sample. And to do this, we're going to use the concept of the friction hill, where at the edge, there is no frictional stresses, and at the center of the sample, there's the maximum frictional force. So what we're actually calculating is the difference between here and here, having no frictional stresses versus having the frictional stresses at x equals 25 millimeters. So when we use the formula for pressure at a certain point, we've got A minus x. Now that's relating to A, half of the distance, minus x, the position we want to see. In this case, where we're calculating the pressure at the very edge for our minimum pressure, we want to find a minus x, while x would be all the way to the edge. So a and x are going to cancel out, meaning this whole term will cancel out, and we'll be left with the same thing as the plane strain yield strength. Next, we're going to calculate the pressure at x equals 25 millimeters. And to do so, for a minus x, we're going to have the total length A, 50 millimeters, minus x, which is 25 millimeters. So this term does not cancel out, and we're left with this. For the last step to find the frictional stress at this point, we take the pressure at the point, subtracting off the pressure from the edge where there would be no frictional stress. And this will be your final answer. Thanks for watching. I hope this helped. Have a great day.